Hello everybody, welcome to the Exam 2 review video quiz. So just like with the last review video quiz we did, you are going to see some series of questions. These are actual questions that I have used in a real exam in the past, and you will answer them. If you get it right, you go to the next question. If you get it wrong, then you'll go to a part of the video where I explain the correct answer. So let's go ahead and begin with the questions. Question 1. So a researcher wants to reject the null hypothesis. The alternative hypothesis is your hypothesis, the one you want. So for example, if my hypothesis is that studying gets you a better grade, then the null hypothesis is studying has nothing to do with getting a better grade. I want to reject that. I want to reject that null hypothesis. The alternative hypothesis would be that studying gives you a better grade. So you want to reject the null hypothesis. Question 2. P-value is none of those. Okay, the p-value is not the same as alpha. Alpha is the standard, right? The probability that you're willing to accept, but it's not the p-value. Okay, and the p-value is not the probability of getting your statistic if your research hypothesis is true. That's not correct either, right? In fact, it's the probability of getting your statistic when the null hypothesis is true, not when your hypothesis is true. So neither. Question 3. I want to know if people with more homework have more stress. What statistics should I calculate? That would be a Pearson's R, which is the lowercase r. Pearson's R is the lowercase r. Now, the reason why is because we're looking at the relationship between two variables, right? Having the amount of homework you have and the amount of stress that you have. As one goes up, the other goes up, or as one goes down, the other goes down. That kind of a relationship is a bivariate correlation that we measure using a Pearson's R. Capital R is when you have more than one continuous variable predicting one continuous variable. And because we only have homework and stress, we can't use R. Now, the reason why we don't use linear regression is because we haven't asked specific amounts. So I didn't say, so a linear regression would be like, if you have exactly 12 hours of homework, what would your stress level be? That would be a linear regression when I would give you an exact amount, and I would expect an exact amount in unstandardized form. Now, a beta is only when you do a multiple regression, and it is the effect of one variable on the other. So it would be like homework on stress, taking out the effect of all other variables. Pearson's R doesn't do that. In this case, you only have two, so you do a Pearson's R. Question 4. All right, so the output above. This is a correlation matrix. Notice how it says Pearson's R. These are Pearson's R values. They are not part of a multiple regression. So this, for example, right here, this number, 0.671, that is the Pearson's R value of the correlation between hours of homework per week and number of credit hours. This p-value, 0.009, is the p-value of that Pearson's R above it. All right? So this particular output is going to show us the effect of credit hours on stress. Where is it? Well, here's credit hours right there. Here's stress right there. So the effect of both is going to be this right there. The combined effect of credit hours and hours of homework on stress? No, because it's only looking at the correlations. It's not looking at a multiple regression. Okay, and C would also require multiple regression. Question 5. I have a hypothesis that people who take more credit hours have less stress. Okay, look above, and based on the output, tell me what I should do. All right, so the hypothesis is that people who take more credit hours have less stress. Let me go ahead and get rid of the markings from last time. So let's get rid of these. Whoop. There. Okay. People who are taking more credit hours have less stress. So I'm looking at credit hours here or here compared to stress. Now, credit hours compared to stress, I don't have anything over on the right, so I have to use this one. Credit hours and stress. 0.589 is the Pearson's R value. The p-value is 0.027. The p-value is 0.027. Whenever we're looking at rejecting or failing to reject the null hypothesis, we want our p-value to be less than our alpha. Alpha, by default, is 0.05 and a two-tailed test, unless I tell you otherwise. So in this case, 0.027 is the p-value of getting 0.589. It's the probability of getting 0.589 when the null hypothesis is true. That's less than 0.05. So we, in this particular case, I would reject the null, except I've got a problem. I got a problem. The problem is that when you look at this output, the hypothesis says, I believe that people who take more credit hours have less stress. Well, take a look at this right here. Pearson's R is a positive 0.589. That means that as people take more credit hours, they get more stress. That would be a negative. If that was a negative, then we would reject the null. But because it's positive, it's going the wrong direction, we have to fail to reject the null hypothesis. Question number 6. All right, so this is a multiple regression. This stuff right here is a multiple regression. And it's asking, based on the output, which of the following is true? All right, so what we're looking at is the combined effect. In this case, I've got credit hours and hours of homework per week on stress. Okay, the dependent variable is stress in this particular case. All right, so the combined effect is capital R. So the combined effect of both credit hours and hours of homework per week on stress is this one right there. The p-value is here. Okay, the p-value is here, and that's less than 0.01. So that's saying that those both together, they do predict. They do predict how much stress people have. So A is not true because it says credit hours and hours of homework together do not predict stress. Well, they do predict stress. There it is. Okay. The number of credit hours you are taking does not predict how much stress you will have if you control for hours of homework. So this question is asking us about something else. This one is going to ask us about betas. This is going to ask us about betas. So these down here, these, for betas, we've got to look down here. Okay, so notice how I have the two different predictors right there. Okay, when we go over to the p-values for these two predictors, here's what we see. Credit hours is over 0.05. That means it does not significantly predict stress when we are controlling for hours of homework. So this right here, this is the beta right here. This is the actual value of the beta. That 0.019 is the effective credit hours on stress when you cancel out, when you take out hours of homework per week. And that is not significant. It is greater than 0.05, so B is correct. The number of credit hours you are taking does not predict how much stress you will have if you control for hours of homework. C, 86% of your stress is predicted by credit hours and hours of homework. That is looking for R squared right here. So this right here, that is the percent of stress that is predicted by credit hours and hours of homework together. So it should say 0.743 if that is correct, and it's not correct. Your stress is predicted by the number of credit hours, but not by the hours of homework. Well, that's not true because look right here, that's not significant. In fact, hours of homework does significantly predict how much stress you have, independent of the number of credit hours you have. That's what that is saying. Okay, question number 7. All right, let's pay attention to this one. So I think that serving cupcakes will make more people come to my party. I have invited 8 people to my party. So that means that n is going to be 8. N equals 8. Whoops, sorry, I forgot. And I have to be on the white for this one. N equals 8. Okay, n equals 8, fine. Normally without cupcakes, I predict that 50% of the people I invite actually come to my party. So that means P equals 0.50, right? The a priori probability of people coming or not coming is 0.50. How many people would have to show up for me to conclude that cupcakes makes people more likely to show up to my party? So for this test, I only think that cupcakes will make people more likely to attend. Now, what that's saying, I do not think that they will make them less likely to attend. That's saying that this is a one-tailed test. I only think they're going to make them more likely to attend, not less likely to attend. And we can assume that alpha equals 0.05. So what this is asking is asking us to look at the binomial. So let's go ahead and look at a binomial. Here's the binomial table. But if you remember, Rn equals 8. So we have to go over here, n equals 8, down here. The likelihood that people are going to show up is 0.50. All right, so that's this right here. And I think that serving cupcakes is going to make people more likely to attend. Now, if my alpha is 0.05 and it's a one-tailed test, then what that means is I am looking at which values of x over here, when you add them together, have a p-value less than 0.05. So what we do is we start with the most extreme. So let's look here. If 8 out of 8 people came, what would be the probability of that happening? Well, if 8 out of 8 people came, then the probability of that happening is 0.003906. So that's less than 0.05. Great. So if 8 out of 8 came, I would reject the null. All right, now let's look at number 7. Okay, so let's look at 7 now. If 7 people came, the probability of that happening is 0.03125. Well, that's less than 0.05, but we can't look at it by itself. We've got to add them up. We've got to add up the probability of 7 or 8 happening. So it's 0.03125 plus 0.003906. That's going to give us 0.034 or something like that. Together, that's still less than 0.05. That means that people could either eat, that 7 or 8 people could come, and we would still reject the null. We would still conclude that serving cupcakes makes people show up. Now, what about 6? When we look at 6, we looked at the probability and it says 0.109. Well, that's already above 0.05. So we know that 6. If 6 won't work. It's got to be 7 or 8 people. 7 or 8 people are the only ones where we would reject the null hypothesis because the probability of 7 or 8 people coming is still less than 0.05. Remember, or means add them up, right? So 7 or 8 people coming, we would add that up. It's still less than 0.05. That we can reject the null hypothesis. So the answer in this case would have to be 7 or 8. Question 8. What's the critical value of t when n equals 22? You can assume a two-tailed test with alpha equals 0.05. All right, so we're looking at a two-tailed test. That's what it says. Two-tailed test, alpha equals 0.05. We need to find the critical value of t. The way we find the critical value of t is by looking at the t table. Now, the thing we need to know is degrees of freedom. Degrees of freedom for what we've been discussing is n minus 2. Degrees of freedom is going to be n minus 2. N minus 2. So we need to look at the degrees of freedom of 20 because n is 22, the degrees of freedom of 20. So let's go ahead and go to the table. Here's the, got to find the table. So that was the z table. We got to go down to a t table. Down to the t table. Here's the t table. Okay, now remember, this is going to be a two-tailed test. So let me go ahead and draw on this a little bit. We're going to do a two-tailed test, right? That means we need to look at this column right here of alpha equals 0.05. But which row do we look at? Well, remember we had 22 people and degrees of freedom is n minus 2. So we need to look at 20 right there. That means that the critical value is 2.086. 2.086. All right, question 9. Now, for the remainder of the questions that we're going to talk about on this exam, we need to look at a scenario. So I gave you data, and here's the scenario. The scenario is that I'm interested in technology. I measure all the variables. The variables are whether or not people have a smartwatch, yes or no. How many cell phones they own, how many laptops they own, how many times they check Instagram per day. The data you have, I have them in a different place than you, are here. So let's just take a look at these data really fast to make sure that you understand what's going on. So number one, we know we have 5 participants. 1, 2, 3, 4, 5. Smartwatch is categorical data because it's either yes or no. So participant 1 does not, participant 2 does not, participant 3 does not, participant 4 does, and participant 5 does. The number of phones you own, I have question marks there. I am not giving you the raw data. But I do have the deviation for phones and the z-score for phones. The number of laptops, also question marks, but I give you the deviations for laptops and the z-scores for laptops. Instagram, times you check Instagram, I didn't give you the raw data, but I did give you the deviations and I gave you the z-scores. This is because I'm so nice, I gave you the product of z-scores between phones and Instagram. All right? Then underneath each one, this is the mean for phones, the standard deviation for phones, the variance for phones, and the same for laptops and Instagram checks. Okay? So that's the way you read this. You do not have any raw scores, but you have all the other information that you might need. So let's go ahead and take a look at these questions. So for this one particularly, let's start with 9. If I have a hypothesis that more cell phones people own, the more they check Instagram. If I conclude that having more cell phones does lead people to check Instagram more, when in reality it doesn't, I would be, so okay, the alternative hypothesis is the more you own, the more you're going to check Instagram. I conclude that the more you own, the more you're going to check Instagram. But in reality, that's not true. The more phones you own does not actually make you check Instagram more. That means that in my conclusion, right here, if I conclude that having more cell phones does lead people to check Instagram, then I've rejected the null. The null is having more cell phones does not make people check Instagram. Okay, that would be the null. And this conclusion rejects that null. If in reality, though, that's not true, that means that the null in reality is true. Okay? So having more cell phones, I go and publish to the world, hey, the more cell phones you own, the more you're going to check Instagram. All right? But in reality, that's not true. I have made an error. And the error that I've made is a type 1 error. Type 1 is when you reject the null hypothesis when the null hypothesis is true. The null hypothesis in this case is that having more cell phones doesn't have anything to do with how much you check Instagram. If I reject that, then I'm saying, hey, guess what? More cell phones, you check Instagram more. If the null is true, though, then I've made a type 1 error. Number 10. I think that one participant who has 10 cell phones has significantly more cell phones than the rest of the group. I only think that 10 is more than the group. I do not think that 10 can be less than the group. Calculate the correct statistic to test this hypothesis using the information at the end of this exam. The information at the end of the exam is the data that we have. Now, in this particular case, one participant has 10 cell phones, right? Well, cell phones is continuous data. So I'm comparing one person to the rest of the group. This is a z-score that I'm trying to create. So let's go ahead and do this. So if I know that my individual has 10 cell phones, okay? My individual has 10 cell phones. So in this case, x equals 10. That moves it for me. I forget that it keeps doing that. Okay, x is going to equal 10. Well, then I need to figure out what is going to be my z-score. Z is x minus x bar over the standard deviation. So I need to do 10 minus the mean, which is 4. So 10 minus 4 is 6. over the standard deviation, which is 3.1622. So 10 minus 4 divided by 3.1622 gives us, I think I've already done the calculation up above. So it is 1.897 or 1.90, right? Okay. So 10 minus 4 divided by 3.16 is 1.897. You can round it up to 1.90. Number 11. Okay, look at the hypothesis statistic you just calculated in the previous question. All right, so I just calculated the z-score of 1.897, which I rounded to 1.90, right? Using the appropriate table, what conclusion should you reach? You can assume that alpha equals 0.05 in this particular case. So what we're looking for then is, what is the probability, what is the p-value associated to a z-score of 1.897, right, or 1.90, all right? So what we do is we look on the table, not the t table this time. Now we're going to look at the z table. So this first table, the normal distribution, we need to find the z of 1.90. 1.90. Here it is right here. And since I only think it can be greater and not less, then I'm looking for the smaller portion, 0.0287. 0.0287. That is the probability of getting this z-score when the person's cell phones are not any different than the rest, right? Okay. All right, so 0.0287 is the right answer for that question. If that's the case, 0.0287 is less than 0.05, so we would reject the null hypothesis. Okay, 0.0287. Remember that the probability of this happening is 0.028, which is a lot less than 0.05. If the hypothesis in the previous question had been two-tailed, what would happen? Well, remember, here's what we got, right? Remember, we looked here and we found that the z-score was 0.19, right? And then the p-value is 0.0287. On a one-tailed test, then this would be less than alpha. But on a two-tailed test, we need to split alpha in half. That means our standard is no longer 0.05. We need 0.05 split in 2, which is 0.025. This is greater than 0.025, so we fail to reject the null because 0.0287 is greater than 0.025. 0.025 is when you split this alpha of 0.05 into two tails. We would fail to reject the null hypothesis if that was the case. Number 13. Number 13. I'm interested in the correlation between between phones and laptops. Okay? I'm going to calculate first the covariance. So first I need to calculate the covariance between phones and laptops. All right. The way you do this is you look at the data. Here's our data. Let's go ahead and get rid of this old X over here. We want phones and laptops. So what we need to do is we actually need to calculate the covariance. Now, covariance is, let me show you the formula for covariance. Covariance is this one right here. It's the sum of x minus x bar times y minus y bar all over n minus 1. I know that's ugly. Let's just show you that again. It is this one, the sum of x minus x bar times y minus y bar over n minus 1. So that means we need to find x minus x bar. Well, in this case, we want phones and laptops. Phones and laptops. So but I don't have any x's. Look over here. Oh, I don't have any. Oh, x minus x bar is the same as deviation. So I already did that for you. I just need to take this deviation, that is x minus x bar, times this deviation, that is y minus y bar. Then I'm going to add them up and divide by n minus 1. So -2 times -2, that's going to give me 4. Okay? Then I've got, where'd my 4 go? I don't know what's going on here. All right, so -2 times -2 is 4. 0 times 0 is 0. -4 times -1 is 4. 2 times 1 is 2, and 4 times 2 is 8. So I need 4 plus 0 plus 4 plus 2 plus 8. So 4 plus 0 is 4, plus 4 is 8, plus 2 is 10, plus 8 is 18. 18. 18. The sum of the product of deviations is 18. I took the deviation for phones times the deviation for laptops. So -2 times -2. Then I added 0 times 0 plus -4 times -1 plus 2 times 1 plus 4 times 2. Those all add up to 18. I divide that by n minus 1. And in this case is 5 because I have 5 participants, so 18 divided by 4. You're looking for 18 divided by 4. And when we look up here at my calculations, come back, calculations. There you are. Okay, 18 divided by 4 is 4.5. So the covariance of phones and laptops is 4.5. 4.5. I hypothesize that there's a relationship between phones and laptops. Good. Calculate the appropriate statistic to test this hypothesis. Now, you can do whatever you want. It doesn't matter, but we just barely calculated the covariance, right? And that was 4.5, okay? So we've calculated covariance of 4.5 already. In fact, I have it right there, 4.5. I calculated that covariance of 4.5. Now, to find Pearson's R, you can use whatever you want, but the easiest one is probably going to be covariance divided by the product of standard deviations. So all we need to do, since we already calculated the covariance of 4.5, is take standard deviation of phones times the standard deviation of laptops. So standard deviation of phones, is right there, 3.1622. Standard deviation of laptops is 1.5811. We multiply those things together, and we take 4.5 divided by that product. So 4.5 divided by 3.162 times 1.581. And when you do that, you get 0.90. 0.90 is R, meaning Pearson's R. 0.90 is the Pearson's R. 15. What statistic did you just calculate in the previous question? That's Pearson's R. Yep, you just calculated Pearson's R. How do we know we did that in the right way? Because I think there's a relationship between phones and laptops. That's 2 continuous variables, not 3, not 4. They're both continuous in this case, and I just want the general relationship. I didn't say if you have 2 phones, exactly how many laptops would you predict I have? That would be a linear regression. So in this particular case, we calculated Pearson's R. Number 16. All right, so in the previous one, we calculated Pearson's R. We calculated Pearson's R 0.90, right? R equals 0.90. That's what we did. Okay, assuming there's a two-tailed test, using the appropriate table, what conclusion should you reach? All right. Now, there's 2 ways to do this. There's an easy way and there's a hard way. So, an easy way is to look at the correlation table. Correlation table is right here. This is the second table in this list, right? If alpha equals 0.05 in a two-tailed test, the degrees of freedom is n minus 2. I had 5 people in my study, right, at n of 5. So the degrees of freedom is 3. That means the critical value of R is 0.878. What that means is that I would need to get something more extreme than 0.878 in order to reject the null hypothesis. Now, I got 0.90. That is more extreme than 878, so I'm going to reject the null hypothesis. So when we go over here, we can reject the null because we got 0.90. We got 0.90, and the critical value of R is 0.878. Now, that's the easy way to do it. The harder way to do it is to calculate the t statistic, calculate the appropriate t statistic, and then figure out what the critical value is for the t. And lucky for us, we're going to do that in the next question. So you're supposed to reject the null, but let's calculate the t in just a second. Question 17. So I need to calculate the t for the question that I just barely did, right? I need to calculate t for the statistic that I calculated in question 14. Remember that that was 0.90, right? So 0.90. So in order to do this, we would get t from R. So we take R times the square root of n minus 2. So in this case, R is 0.90. All right, n minus 2, n is 5. So n minus 2 is 3. Okay, how do I know that n is 5? Well, remember, let's look at the data. I have 1, 2, 3, 4, 5 participants, n is 5. Okay. So, all right. So I need 0.90 times the square root of 3 divided by the square root of 1 minus R squared. Okay? 0.90 times 0.90 is 0.81. Let me just make sure that I'm doing my math right. Yep, 0.81, of course. So 1 minus 0.81 is going to give us 1 minus 0.81. So that's going to give us the square root of 0.19. And when you do those calculations, you end up with 1.5588. So 0.90 times the square root of 3 is 0.15588 divided by the square root of 0.19, which is 0.435. And then you get 3.58. That's going to be our t. Our t is going to be 3.58. Okay? Let me just check my math. Yep, looking good. So 0.358 is the right answer. Now, when we look at that on the t table right here, the degrees of freedom that we've been working with, that would be, the degrees of freedom would be 3 because we had a n of 5, right? That means for a two-tailed test, we would need to get a t value of at least 3.182 in order to reject the null hypothesis. And so we got a 3.58. 3.58 is more extreme. It's farther away from 0 than 3.182. So we would reject the null hypothesis. Okay, question 18. That's exactly what we were just discussing. Looking at the statistic that you just barely did with t, assuming this is a one-tailed test and use the appropriate table, what would you conclude? Well, you would reject the null, right? If it's a two-tailed test, you reject the null. If it's a one-tailed test, you definitely reject the null. But in case you were trying to figure it out, the t that we barely calculated is 3.58. All right, 3.58. Now, the degrees of freedom, let's go ahead and erase this. The degrees of freedom here is going to be 3 because it's n minus 2. We had 5 people in this in study, so our degrees of freedom is 3. Now, in this case, we were talking about a one-tailed test. So that means we need to look at this. We need to look here at this column. That means we need to get a t-value of at least 2.357. We got 3. What was it? 58? We got 3.58, and that's a lot more than 2.35, so we get to reject the null hypothesis. Reject the null hypothesis. Question 19. I think that more phones people own, the more likely they are to check Instagram. So now I'm looking at phones and Instagram. Okay, now I didn't give you specific numbers, so this is not a linear regression. I want a Pearson's R for this one. So more phones people own, the more likely they are to check Instagram. Now let's take a look at our data. I need the R between phones and Instagram if this is the case. Come back to me. All right, so let's get rid of some of this stuff. Now, in this particular case, I was super nice to you, and I actually calculated it for you, right? The product of z-scores between phones and Instagram, there it is right there. Well, if you're looking for the way you can calculate this, we have several different ways that we can calculate z. So this works to calculate z, R, I'm sorry. These both work to calculate R. In fact, this also does. But I was expecting you to use this one because I already gave you the product of z-scores. So you just need to add them up and divide by n minus 1. I'm just asking you to add up 0.5163 plus 0 plus 0 plus 0 plus 2.0655. Then divide that by n minus 1. N is 5. N minus 1 is 4. Add these up, divide by 4. And you will get right here. Add them up, divide by 4. You get 0.6454972. That is 0.65. 0.65. Okay. This is 0.65, and that is going to be R. Number 20. Look at the hypothesis and statistic you calculated in the previous question. Using the appropriate table, what conclusion should you reach? You can assume two-tailed test with alpha equals 0.05. All right, so remember, I've got n of 5, degrees of freedom is n minus 2. I don't have to go through all of that with the t-table if I don't want to. I want to make it easy for myself. I'm going to use this correlation table instead. And so in order to use this correlation table, I just look and say, okay, my degrees of freedom is 3. My degrees of freedom is 3, right? Because it's n minus 2 and n is 5, right? We have 5 people. That means I need to get a P, I need to get an R of at least 0.878, at least 0.878 or negative 0.878 in order to reject the null hypothesis. Now we just barely calculated an R statistic of 0.65. 0.65, that's not good enough. 0.65, that's not going to work. That's not more extreme. We have to fail to reject the null. All right, good. 20. Look at what we just barely did. Using the appropriate table, what conclusion would you reach? You can assume, oh, that's what we just barely did. Sorry, that was 20. 21. If I think that the number of phones you own could predict the number of laptops you own, and I calculate the slope. All right, how are we going to calculate the slope? Well, the easiest way to calculate the slope, let's look at these tables right here. Get rid of some of this. Okay. The easiest way that we are going to calculate the slope is right there. The covariance divided by the variance, which is the standard deviation squared of x. Okay? So we just need to divide the covariance by the variance of x. Now, what was x in this case? Let's take a look. We just barely told you that the number of phones you own could predict the number of laptops. Well, guess what? Phones and laptops, we already calculated the covariance of that. Did we not? Yes, we did. It was 4.5. We calculated that covariance before. We got 4.5. All right, so we know that the covariance is 4.5 because we already calculated it in previous question. Now, what we need to do is take the standard deviation of x, which is phones, and square it. Well, look at that. The variance is the standard deviation of phones squared. So we have it right here. All we have to do is take the covariance that we already calculated, 4.5, divided by the variance, 10. 4.5 divided by 10 is 0.45. 0.45. Where is it? There it is, right there, 0.45. If you think the number of phones you own, 22. If I think that the number of phones you own could predict the number of laptops you own, calculate the Y-intercept. All right, well, let's calculate the Y-intercept. In order to do this, we take the mean of Y minus the slope times the mean of X. All right, in this case, Y is going to be laptops and X is going to be phones. So what we want to predict is laptops. So that means it's going to be Y, right? So then we need the mean of laptops minus the slope. We just barely calculated that slope, 0.45, times the mean of phones. We look at these data down here. Here's what we get. The mean of Y is laptops, so 2 is the mean of Y, minus the slope, 0.45, times the mean of X, which is 4. When we do that, we get 0.20. 2 minus 0.45 times 4. That is 0.20. That is the Y-intercept. That's how many laptops I assume you'd own if you own 0 phones. 23. Mo has 0 phones. How many laptops do you predict he's going to have? Guess what? That's the Y-intercept. That's what you just barely calculated. You just barely calculated that. So barely, if you want to go through, you can figure it out, right? You can do Y equals mx plus b, which is Y equals bx plus a, is what we say nowadays, right? So Y equals b. B is the slope. The slope is 0.45 times x. Well, x is 0 in this case, so it'd be 0. Plus the Y-intercept. Y-intercept is 0.2, but you don't even need to do that because the Y-intercept is the amount of laptops, the amount of Y when you have 0 of x. That is the entire point of the Y-intercept, 0.20. You would expect him to have 0.20 laptops. 24. May has 11 phones. How many laptops do you predict May will have? All right, let's use that formula for the line, Y equals bx plus a. Y in this particular case is what we're trying to figure out. B is 0.45, right? We just calculated it before, 0.45. 0.45 times x, x is 11 in this case, plus a is 0.20, that's the Y-intercept. So 0.45 times 11 plus 0.2, you get 5.15. If May has 11 phones, we would predict that she has exactly 5.15 laptops. That's a linear regression. 25. What's the critical value of Z for a two-tailed test when alpha equals 0.05? All right, so we need to look at the Z table, but it's two-tailed. It's two-tailed. That means we need to split that 0.05 into 2 parts, 0.025 and 0.025. So what we're looking at is we're looking for the value of Z that has a probability of 0.025. 0.025. So we'll look over here. Let's find the Z table. It's up here. And we're looking for the smaller portion, right? Because we need, this is one tail. We need to split that in 2. So we're looking for this to equal 0.025. 0.025. And let's go erase these that we've had before. Erasing this because that's not it. 0.025 is right here. That's 0.05 split into 2 tails. And so the value of Z is 1.96. The critical value of Z when alpha equals 0.05 in a two-tailed test is 1.96. Okay. 26. The probability of getting a statistic when the null hypothesis is true is, that's your p-value. The probability of getting the statistic when the null hypothesis is true. That's the p-value. Alpha is the standard that you have, the standard that your p-value has to meet. You get to make up alpha. P-value you don't get to make up. The critical value is the value of the statistic, right? The value of T or R or whatever happens to be that you have to meet in order to reject the null. And the covariance is the covariance. It's when you multiply the deviations of two variables, you add them up, divided by n-1. 27. Covariance is, it's used to calculate R. Now, we also use it to calculate B. And then we use B to calculate A, but you don't have to use it, that's for sure. But we use it to calculate R. We can also use it to calculate B. And then we use B to calculate A. 28. You would not use a sampling distribution to tell you alpha. You make up alpha. Sampling distribution is a distribution of all the values of a statistic and the probability of them happening if the null hypothesis is true. That is the sampling distribution. Alpha is whatever you make up, right? You decide what alpha is going to be. Generally, it's 0.05. Doesn't have to be, though. 29. The value of the statistic that is the same p-value as alpha is the critical value. The value of the statistic. So, for example, the value of t that has the same p-value as whatever alpha you chose, that would be the critical value of t. You have to get at least that t or greater or more extreme in order to reject the null hypothesis. And 30. If the null hypothesis is true, the most probable value of R that you would get is 0, because 0 means that there's nothing going on. There's no relationship between the two variables. The most probable value would be 0. Okay. Thanks, everybody. Good luck.